These are the mysterious ruins of Puma Punku, nearly 13,000 feet in the Altiplano of Bolivia. What you have here are massive blocks of granite scattered like some kids.
What is Puma Punku? Puma Punku sits on the Bolivian Altiplano, the high plateau of the Andes at an elevation of approximately 12,800 feet above sea level. It is part of a larger complex called Tiwanaku, which was a major pre-Columbian civilization that most people outside of South American archaeology have barely heard of. And honestly, that invisibility is its own kind of crime, because what was built here makes some of the most celebrated ancient sites on Earth look straightforward by comparison. The Altiplano at this elevation is brutal. The air is thin. The temperature swings between freezing nights and intense solar radiation during the day. The landscape is largely treeless. There is no obvious reason why anyone would choose this location to build anything, let alone one of the most structurally complex stone assemblages in the ancient world. And yet, here it is. The site covers an area of roughly 400 by 200 meters and is littered with enormous carved stone blocks. Many of them are now scattered and tumbled, as though something catastrophic disrupted the original construction. Some of these blocks weigh over 100 tons. The largest, sometimes called the plataforma, is a single red sandstone slab estimated at around 130 tons. Moving that stone to this location from the nearest quarry, which is approximately 10 kilometers away, is a challenge that modern engineers would approach with significant logistical planning. How it was moved without wheeled vehicles or draft animals in this terrain is a question that has never been satisfactorily answered. But the sandstone blocks, as impressive as they are not what makes Puma Punku uniquely disturbing. The sandstone at least has a conventional hardness. You can imagine, if you stretch your imagination considerably, how stone tools might work on it given enough time and labor. The H blocks are different. They are made from andesite. Andesite is a volcanic igneous rock that registers between 6 and 7 on the Mohs hardness scale. That is harder than iron. It is harder than most of the tools that conventional archaeology assumes were available to the builders of Puma Punku. And what was done to this stone, the shapes cut into it, the tolerances maintained, the geometry achieved, is what the 3D scanning project has now documented with a precision that makes the traditional explanation genuinely untenable. The site was first formally studied by European researchers in the 19th century. By 1945, archaeologists had begun serious excavation. The ruins you see today are the result of both ancient destruction, possibly from a catastrophic flood or seismic event, and centuries of locals using the site as a convenient quarry for building materials. Blocks that once formed part of one of the most sophisticated structures ever built were carried away to construct churches and houses in nearby towns. The scale of what was lost is incalculable. What remains is enough to make the point. The H blocks, what we thought we knew. The H blocks are the signature feature of Puma Punku. They get their name from their cross-sectional shape, which from the right angle resembles the letter H. Each block is roughly the same dimensions, approximately 80 centimeters tall, 60 centimeters wide, with internal channels, recesses, notches, and flanges cut into the stone with extraordinary consistency across multiple individual pieces. What makes them immediately strange to anyone who looks carefully is the repetition. These are not rough approximations of a similar shape. They are functionally identical, block after block after block. The internal geometry matches with a uniformity that looks less like handcraft and more like manufacture. For decades, the conventional explanation was that these blocks were shaped by skilled craftspeople using stone tools, possibly supplemented by harder stone abrasives over long periods of time. The argument went something like this: given enough skilled labor, given enough time, given enough patience, you can achieve impressive results with simple tools. We see this in other ancient cultures. The Egyptians shaped granite. The Maya carved intricate limestone panels. Skilled hands working hard stone over extended periods can produce surprising precision. This explanation was accepted not because it was demonstrated to be correct, but because it was the only explanation that fit within the framework of what we believed was technologically possible in pre-Columbian South America. There were no metal tools found at the site consistent with the kind of hardness needed to cut andesite efficiently, no abrasive compounds, no drilling equipment. The tools that should have been required for the work that was done here are simply absent from the archaeological record. I want to be fair to the mainstream interpretation. Absence of evidence is not evidence of absence. Tools degrade. Organic materials rot. Metal corrodes. The fact that we have not found the right tools does not prove the right tools did not exist. That is a legitimate point and it deserves acknowledgement. But here is the problem. It is one thing to say skilled hands with stone tools could produce impressive results given unlimited time. It is another thing entirely to say skilled hands with stone tools produced results that are in some measurable ways indistinguishable from modern machine components. And that is precisely what the 3D scanning data is now showing us. The 3D scan project. The scanning project that produced these findings was not a single dramatic expedition. It was a methodical multi-phase documentation effort using a combination of terrestrial laser scanning, structured light scanning for close-range surface detail, and photogrammetric modeling to create composite three-dimensional records of individual H-blocks at sub-millimeter resolution. I want to explain what sub-millimeter resolution actually means in practical terms, because it matters for understanding why this data is different from anything collected before. Previous studies of Puma Punku relied on physical measurements taken with calipers, rulers, and manual recording. Those methods are good. They have produced valuable data, but they have limitations. You can measure what you can access. You can record dimensions on visible surfaces. What you cannot do easily with manual measurement is capture the full three-dimensional geometry of complex internal recesses, undercut channels, and nested joints that are partially hidden by the surrounding stone. The 3D scanning technology changed this completely. By projecting structured light patterns onto the stone surfaces and recording how those patterns deformed across the geometry of the block, researchers could reconstruct the complete three-dimensional shape of features that were previously invisible to conventional measurement, including features buried inside recesses that no tool, no human hand, and no eye could directly access during cutting. Let me say that again because it is important. The scanning revealed geometric features inside the internal channels of these blocks that were cut in locations where no conventional tool could have been guided by direct observation or direct hand control during the manufacturing process. The team that conducted the primary scan analysis included engineers with backgrounds in precision manufacturing and metrology, the science of measurement. These were not archaeologists working outside their training. These were people whose professional lives are built around understanding what it takes to produce precision geometry in hard materials. When they looked at what the scans were showing them, their reaction was not excitement. It was confusion, and then, methodically, a kind of quiet alarm. Finding 1. The internal geometry. Here is what the scans found. And I am going to be as specific as I can, because the specifics are where the story lives. Inside the H-blocks, there are internal channels, recesses cut into the stone that form part of the interlocking system. These blocks were clearly designed to interlock. These channels run partially into the interior of the block, meaning they are not simply surface cuts. They go deep, and at the terminus of these channels, at the innermost point of the recess where the cutting stopped, the geometry is not rough. It is not approximate. It is precise in a way that defies the limitations of the tools we attribute to the builders. The 3D models revealed that at the deepest interior points of these recesses, the corners are square to tolerances of less than 0.2 of a millimeter. The walls are flat to tolerances of less than 0.3 of a millimeter across spans of 15 to 20 centimeters. The floor of the recess meets the walls at consistent angles maintained to within half a degree across multiple separate blocks. Now pause on that for a moment. Square interior corners cut deep into andesite, maintained to sub-millimeter tolerances. If you want to understand why that is disturbing, go to a modern machine shop and ask them to produce that result in a comparably hard material. They will do it, of course, because they have carbide tooling, computer numerical control systems, and precision measurement equipment. They will also tell you it is not trivial. It requires planning. It requires controlled material removal. It requires the ability to measure what you are doing at every stage of the process. Now ask yourself how you achieve that result by feel in the dark interior of a stone recess, using stone tools or copper chisels on andesite that is harder than the tools you are supposedly using. The conventional explanation has no mechanism for this. There is no proposed technique from the experimental archaeology literature that demonstrates how interior corner precision of this quality can be achieved in hard volcanic stone without guided cutting equipment of some kind. And nobody has successfully replicated it. Not even close. What makes this even harder to dismiss is the consistency across individual blocks. This is not one anomalous piece that might represent a unique achievement by an unusually gifted craftsperson. The scanning team measured this interior precision across more than 30 individual H blocks and found the same tolerances repeated, the same geometry, the same quality of surface finish at the same deepest interior points where direct tool guidance would have been most difficult. 30 blocks. Same result. That is not luck. That is process. Finding 2. The repeating tolerances. The second major finding from the scan data builds directly on the first, and in some ways it is even more unsettling because of what it implies about how these blocks were made. When the engineering team analyzed the dimensional data across the full sample of scanned blocks, they ran a statistical analysis of the variance in key measurements: width of internal channels, depth of recesses, angles of flanges, height of the interlocking ridges, thickness of the H crosspiece. What they found was a coefficient of variation, which is a statistical measure of consistency relative to the mean, of less than 1% across most critical dimensions. For those of you who do not spend your weekends reading metrology literature, which I am assuming is most of you, and honestly, good life choice, a coefficient of variation under 1% means the measurements are extraordinarily consistent. It means the variation from block to block is so small that it falls within what modern manufacturing would consider acceptable tolerance for precision components. Let me put a comparison on the table. The H blocks at Puma Punku show dimensional consistency comparable to machine components produced with guided cutting processes, not hand-shaped stone, not individually crafted artisan work. The statistical fingerprint of these blocks looks like batch production using controlled tooling. Here is the part where I want to be honest about something that is slightly uncomfortable. When I first read this finding, my instinct was to reach for a conventional explanation. Maybe the blocks were shaped using templates, physical guides that workers could use to check their dimensions as they went. This is not an unreasonable proposal. We know ancient Egyptians used templates and set squares. There is good evidence that systematic measurement was part of how ancient builders achieved precision. But templates explain surface geometry. They do not explain interior geometry in recesses where you cannot physically place a template against the surface you are cutting. They do not explain how you maintain flat walls and square corners inside a channel that is 15 centimeters deep and barely wide enough to insert a tool. And they absolutely do not explain how you achieve this result in andesite, which resists cutting with such ferocity that a modern angle grinder loaded with a standard abrasive disc will barely scratch it. The repeating tolerances across 30-plus blocks are telling us something specific. They are telling us that whoever made these blocks was not doing it freehand, one block at a time, checking by eye and experience. They were using a process that controlled the geometry systematically. A process that produced the same result reliably, repeatedly, across an entire production run. We do not know what that process was. That is the honest answer. We do not know. But we know it was not stone tools and patience, because stone tools and patience do not produce a coefficient of variation under 1% in andesite interior channels. The math simply does not work. Finding 3. The interlocking logic. The third finding from the 3D scan project may be the one that changes the conversation most permanently, because it moves beyond the question of how these blocks were made and into the question of why they were made the way they were. when the scanning team created digital models of multiple H blocks and began virtually assembling them, testing how they fit together in different configurations, they discovered something that previous researchers had suspected but never been able to fully document. These blocks were not designed to stack. They were designed to interlock. The difference is enormous. Stacking is simple. You place one block on top of another, and gravity and mass keep them in place. Almost every ancient stone construction we know of works this way at its fundamental level. Weight plus contact equals stability. Interlocking is a different engineering philosophy entirely. Interlocking means the blocks are physically locked to each other through their geometry. They cannot be separated by horizontal force without first lifting them vertically out of the joint. The joint itself carries structural load in multiple directions simultaneously. This is how modern precision engineering connects components that need to resist movement in more than one axis. The H blocks at Puma Punku, according to the 3D scan analysis, incorporate interlocking joint geometry that would require the blocks to be assembled in a specific sequence, lowering each block vertically into position so that its internal flanges slide into the receiving channels of the adjacent block. Once in place, the assembly would have been resistant to horizontal displacement from any direction. Think about what this means for a structure at 12,800 feet above sea level in one of the most seismically active regions on Earth. The Andes are not gentle terrain. Earthquakes are common. Ground movement is a real and persistent threat to any structure. An interlocking block system that resists horizontal displacement is not accidental over-engineering. It is a deliberate design response to a real environmental challenge. Whoever built Puma Punku understood seismic engineering. They understood that horizontal ground movement was a threat to their structure, and they designed their primary building components to mechanically resist that threat through geometry rather than just mass. That is sophisticated structural thinking. It implies not just skill, but theory, an understanding of forces and how to counter them that we would not expect from a civilization at the developmental stage we typically assign to pre-Columbian Andean cultures. And there is one more detail from the interlocking analysis that I cannot leave out, because it is the one that made the engineers on the scanning team go quiet. The tolerances required for the interlocking joints to function correctly are tighter than the tolerances required for the internal geometry alone. The flanges that slide into the receiving channels have a clearance fit measured in the scan data of approximately 0.3 of a millimeter. A clearance fit, for context, is the intentional gap between two mating components that allows them to be assembled without binding while still maintaining close contact for structural purposes. 0.3 of a millimeter clearance in andesite, repeated across multiple joint locations across multiple blocks, is a clearance fit that a modern precision machinist would recognize immediately as deliberate and controlled. It did not happen by accident. It was designed. The timeline problem. Now we need to talk about when Puma Punku was built, because the answer to that question is significantly more contested than most people realize, and the scan data adds a new layer to a debate that was already complicated. The conventional archaeological dating places the main construction phase of the Tiwanaku complex, including Puma Punku, between approximately 500 CE and 1000 CE. This dating is based primarily on radiocarbon dates from organic material found at the site and stylistic comparisons with other Andean archaeological sequences. But here is where it gets complicated. Radiocarbon dating at Puma Punku has produced results with an extremely wide range. Some dates cluster in the first millennium CE, others push back significantly further. The site has been occupied, modified, and reoccupied across a very long period, which makes it difficult to establish clean dates for specific construction phases. A Bolivian archaeologist named Arthur Poznansky spent decades studying Tiwanaku in the early 20th century and proposed, based on astronomical alignment analysis, that parts of the complex dated to as far back as 15,000 BCE. His methods were criticized by mainstream archaeology, and his conclusions were largely dismissed. But the astronomical alignment data he used has never been fully refuted. It has simply been set aside, the way inconvenient evidence often is when it threatens a tidy narrative. More recently, geological analysis of the site has identified evidence of a catastrophic flood event that appears to have disrupted the original construction. The nature and timing of this event is disputed. Some researchers connect it to the well-documented lake transgression of Lake Titicaca, which sits only 15 kilometers from the site. Others see evidence of something more dramatic and more ancient. What the 3D scan data adds to this debate is a technical argument. If the precision engineering visible in the H-blocks required tool technology more advanced than what was available in the first millennium CE in the Andes, then the blocks either predate the conventional chronology or they represent a technological capability that our current model of Andean civilization development cannot accommodate. Neither option is comfortable for mainstream archaeology. Both options demand serious investigation. There is also the question of the site's condition. The H-blocks and other precision-cut stones at Puma Punku show extreme weathering consistent with very long exposure. Some researchers have argued the degree of erosion visible on certain stones is inconsistent with an age of only 1 to 2,000 years in the Altiplano climate. This argument is difficult to quantify precisely, which is why it remains controversial, but it has not been disproven either. The honest position is this: we do not know with certainty when Puma Punku was built. The conventional date may be correct. It may not be. But the 3D scan findings add urgency to this question. Because if the technology visible in these blocks did not exist in the first millennium CE Andes, then the date we have assigned to this site has to be wrong. What mainstream archaeology says. I want to give the conventional interpretation a fair hearing here, because intellectual honesty requires it, and because some of the skeptical arguments are genuinely worth taking seriously. Mainstream archaeology's response to claims about Puma Punku's impossible precision generally takes two forms. The first argument is that the precision is overstated. Traditional archaeologists point out that many claims about Puma Punku circulate online without careful verification of the actual measurements being described. Some of the more dramatic assertions, tolerances of a fraction of a millimeter across large surfaces, perfectly flat faces across meters of stone, have been challenged as exaggerations or misinterpretations of what the blocks actually show. This is a fair challenge, and it is exactly why the 3D scan data matters. Because now we have numbers. The scanning team's methodology is documented. The measurements are reproducible. You cannot argue with a point cloud. The precision that the scans record is the precision that exists in the stone. It is not an impression or an interpretation. It is a measurement. The second mainstream argument is the skilled labor plus time explanation, which I described earlier. Given the organizational capacity that the Tiwanaku civilization clearly possessed, given evidence of large-scale food production and population centers, it is argued that skilled stone workers with sufficient time and motivation could have produced these results with the tools available. This argument has never been experimentally demonstrated. No research team has successfully replicated the interior joint precision of an H-block using period-appropriate tools. The experimental archaeology that has been attempted with Puma Punku-style cuts in comparable stone has consistently produced results that fall far short of what the scans document. That gap between what the conventional theory claims is possible and what controlled experiment has been able to demonstrate is where the real scientific problem lives. What the scan cannot explain. Let me be direct about the three things the scan data establishes that no conventional model currently accounts for. First, interior corner precision in andesite at sub-millimeter tolerances, achieved in spaces where direct tool guidance was geometrically impossible using any known ancient technique. The scans document this. The conventional explanation has no mechanism for it. Second, statistical batch consistency across more than 30 individual blocks, indicating a controlled production process rather than individual hand craftsmanship. The coefficient of variation in critical dimensions falls within modern manufacturing standards. No proposed ancient technique produces this result in hard volcanic stone. Third, clearance fit interlocking joint geometry designed and executed to tolerances that imply the builders understood fit and function in an engineering sense, not just an aesthetic or symbolic sense. These joints were designed to work mechanically. They demonstrate an understanding of tolerance engineering that we do not associate with any pre-Columbian culture. These three findings do not prove any particular alternative theory. They do not prove that Puma Punku was built by a lost advanced civilization. They do not prove ancient technology of a specific kind. They prove something more limited and more important. They prove that the conventional explanation is insufficient. The current model does not account for the evidence. And in science, when your model does not account for the evidence, the correct response is to revise the model, not to ignore the evidence. The bigger picture. Puma Punku does not stand alone. This is something that becomes increasingly difficult to dismiss the more sites you look at carefully. In Egypt, the precision cutting visible in the Aswan granite quarries, the kind that AI analysis recently flagged as inconsistent with dolerite pounding methods, shows the same pattern of interior precision in spaces where direct tool guidance was restricted. In Turkey, Göbekli Tepe was built approximately 12,000 years ago by a culture we had previously assumed lacked the organizational capacity for monumental construction. The site's existence forced a fundamental revision of our timeline for complex human society, and that revision is still working its way through the literature. In Peru, the Inca sites at Cusco and Sacsayhuaman show polygonal stone fitting of such precision that a sheet of paper cannot be inserted between adjacent blocks. The conventional explanation, patient shaping with stone tools and repeated test fitting, has the same problem the Puma Punku explanation has. Nobody has demonstrated it experimentally at anything approaching the quality visible in the actual structures. What you see when you look at these sites together is a pattern, precision that exceeds the demonstrated capability of the proposed tools, geometric consistency that implies process control rather than individual craftsmanship, engineering solutions to structural problems that require not just skill but theory, and in many cases, a timeline that either predates the civilization credited with the construction or sits uncomfortably at the edge of what the civilization's developmental stage should allow. The pattern is not proof of a single explanation. Maybe each site has its own unique story. Maybe there are conventional solutions we have not yet imagined. But the pattern is real, and it is asking a question that keeps getting louder. What do we actually know about the capabilities of ancient human civilization? And how much of what we think we know is assumption dressed up as conclusion? What this means. Jeremy Wade, in the years after River Monsters ended, described himself as a witness, someone who had been in the right places at the right time to see something that most people were not looking at, and who had the responsibility to report honestly what he saw rather than what was comfortable to say. I think about that framing when I look at the Puma Punku scan data. The blocks have been sitting on that altiplano for centuries. The precision has been there the whole time, carved into andesite at 12,800 feet above sea level, waiting for us to develop the tools to measure it properly. Now we have those tools. Now we have the measurements. Now we know what is in there. The internal joints should not exist. Not according to the model we use to explain this site. Not according to the tools we say were available. Not according to the timeline we have assigned. They should not exist. And yet the point cloud data is unambiguous. The tolerances are there. The clearance fits are there. The batch consistency is there. We have a choice now. The same choice that comes up every time the evidence at one of these sites gets measured carefully enough to be undeniable. We can defend the existing model, find reasons to question the data, propose untested mechanisms that might bridge the gap between what our theory predicts and what the scans show. Or we can let the evidence lead. The stones at Puma Punku have been trying to tell us something for a very long time. They were shaped by someone who understood precision engineering, someone who had a controlled production process for hard volcanic stone, someone who designed interlocking joints with clearance fits measured in fractions of a millimeter, Someone who built a structure at extreme altitude in a seismically active region and engineered it specifically to survive ground movement. We do not know who that someone was. We do not know what their tools looked like. We do not know with any real certainty when they lived. But we know what they left behind. We can measure it now. We can hold the numbers in our hands and read them clearly. The question is whether we are willing to follow those numbers wherever they lead, even if where they lead is somewhere that forces us to rewrite what we think we know about the past.